Okay, hello everyone. These are the notes for section 6.3. I decided to go ahead, although you were supposed to do the definitions on your own, I decided to post these definitions in the video. So you can pause the video and then copy down the definitions. Okay. All right. So this section is dealing with the central limit theorem. And in statistics, that's one of the main theorems. So if someone, if you tell someone you've taken a statistics course, they will assume that you know about the central limit theorem, okay? Amongst other things, but it's a main theorem, and that's what we're talking about in this section. And it's not difficult to understand. It's sort of similar to what we've been dealing with in terms of our normal distribution. So you still will need your table. And in fact, you make sure you have your table handy when you're going over these video notes. Okay, the Z table. All right, so sampling distribution of sample means, that definition. So a distribution using the means, oh, that's too big. The means computed from all possible random samples of a specific size taken from a population. So now we're talking in terms of our samples, right? Because in the last section, when we did the applications, we were given the population mean and population standard deviation. But the reality of it is, for the most part, you'll be dealing with samples of data and not the actual population data. Okay, so sampling distribution of sample means. The sampling error is the difference between the sample measure and the corresponding population measure, due to the fact that the sample is not a perfect representation of the population, right? So there's going to be error if you just take a sample. However, there are ways to minimize that error in terms of how you look at your distribution and the number of sample points you take. Okay, so the two properties of the distribution of sample means: one, the mean of the sample means. So the mean of the means will be the same as the population mean. Okay, so if you take a whole bunch of different samples and you have a whole different samples, take their means, and then you take the average of those means, then that's going to be the same as the population mean. Okay, the standard deviation of the sample means will be smaller than the standard deviation of the population. Okay, and it would be equal to the population standard deviation divided by the square root of the sample size. So that formula is sort of taking into account that we're using a sample. Okay, so the standard deviation of the sample means is also called the standard error of the mean. And so, like I said, it is the standard deviation divided by the square root of n. Okay, and so this, as we know, is the population standard deviation. And I'll use some shorthand notation. Okay, so it's sigma over the square root of n. Okay, I want to make sure you got that. All right, and that x bar, so x bar is represent our sample means. Okay. So the central limit theorem states that as your sample size, so sample size is n, as that increases without the limit, okay, so it sort of goes on and on, the shape of the distribution of the sample means taken with replacement from a population with mean mu, standard deviation sigma, will approach a normal distribution. Okay, and as previously shown, this distribution will have a mean, mu, and a standard deviation. This will make more sense as we apply it into our problems on what it's really stating. I know it's a lot of wording there, but we'll look at examples. Oh, okay, so I also wrote this one out as well. So draw and interpret figure 6.633, distribution of sample means for a large number of samples. Write down the two important things to remember when you use the central limit theorem. Okay, so I wrote this out. You can also, to receive more information, you can look in the book as well. All right, so the two things when you use the central limit theorem. One is that when the original variable is normally distributed, okay, the distribution of the sample means will be normally distributed as well for any sample size n. Okay, so in other words, if you know that is a normal distribution or normally distributed, then for any sample size n, so you don't have to have a minimum number of sample points. If it's normally distributed, then you can just go ahead, you can just go straight forward, right? When the distribution, so that's for 1. 2, when the distribution of the original variable is not normal, okay, if it's not normal, and so if you don't know, if it's not giving you any information on whether it's normal or not, then you assume that it's not normal, right? And in that case, you need a sample size of 30 or more. And that's what I was telling you all in your research, although I'm tweaking that. I'm gonna send something out about the template and things, and so I'm changing that because of just the time. We don't really have the time. All right. But in general, just know as you move forward in your majors and you have to do research, that if you don't know you have a normally distributed sample, then you need to, and again, you can use what we talked about in the last section. You can draw a histogram to kind of see if your data points follow this normal curve, or you can use the PC, the Pearson coefficient of skewness, to talk about that. So you could look at it that way. But when it's not, or you can't determine it, then you need 30 or more is needed to use a normal distribution to approximate the distribution of the sample means. The larger the sample, of course, the better your approximation will be, right? And so this is our, as you know, this is our normal distribution graph, curve, and sort of bell-shaped, right? And we know here that this coincides with 68% of our data, right? And here is, okay, and so that's one standard deviation. We know that at 2 standard deviations away, that represents 95% of our data. And then at 3 standard deviations away, we get 98% of our data. Okay. And so this is what we need to take into account when using the central limit theorem. Okay. So now so we've done these before. It's just now we have to keep in mind we're looking at sample means. So we have to keep in mind a different Z formula. Z formula. And I think I might have put it in 6.1, but I'm going to restate it again in this example too. Okay. All right. So let's look at this example. A Nelson report says that children ages 2 through 5 watch an average of 25 hours of television per week. Assume that the variable is normally distributed. Okay. And so we're given that. Okay. And the standard deviation is 3 hours. Okay. If 20 children between the ages of 2 and 5 are randomly selected, find the probability that the mean number of hours they watch television will be greater than 26.3. So the mean number of hours. Okay. So that is our sample means. Okay. And so let's see what information we have. Okay. So we have mu, a population mean, is 25. Sigma is 3. N is 20, right? That's our sample size. And so, which is fine because we're told it's normally distributed, right? If we weren't given that, then we would need 30 or more data points, okay, samples, children, I should say, whatever your participants, whoever your participants are, okay? And so now X bar sample mean is 26.3, okay? And so we know it's a normal curve. So let's draw a normal curve, right? And we know mu is 25 and X bar is 26.3. And we want to know will be greater than. So we're looking to the right, okay? And now the Z, we have to be careful because since we're talking about sample means, our Z score will be X bar minus mu over sigma over the square root of n, okay? Because we're looking at this so this is how we are using the central limit theorem, okay? And this is remember that's our standard error of mean. So when we're referring to means or sample means, you're using this as your z-score, as opposed to if you go back to the wording of 6.2, we didn't even talk about means in those problems, right? And so we use just the regular formula to figure out our z-score. Okay, and so we know our values, so just plug it in. 26.3 minus 25, right, divided by 3 divided by the square root of 20, and let's round to 2 decimal places, and you should get, I believe, 1.94. Always double check my answers because there could be a mistake, and if there is, just let me know in class. So 1.94 is our z-score, right? But we have to be careful because the same rules still apply. It's shaded to the right. Our table only gives us information to the left. So once you find that area, so the area of our z is 0.9738, or the probability, right? They're interchangeable. So it's going to be 1 minus 0.9738, which is 0.0262. And so we would say thus 2.62% of the children selected watches 26.3 or more hours of TV per week. Okay. All right. So I'm going to stop this video here and do another video to finish the problems. I don't like my videos to run over 15 minutes. I feel like any more than that, and you guys sort of tuned out. Hopefully you haven't tuned out now. But I'm going to stop here and we'll finish the remaining examples in another video.